Great. Thank you, Chris. Thanks for having me. Hope your time here in Seattle has been great, same as your time here at the conference. We're right here in Seattle ourselves at Blue Origin, and it's actually so great to see so many more space people here of all parts of the community. So welcome, and it's actually exciting to actually tell you a little bit about Blue Origin. It's going to be a bit of a recap for some of you, but hopefully you'll find some more information about what we've been up to. But I'm particularly excited to be telling you a bit more about Blue Moon, our lunar lander, which we've been working on for quite a while, and my team in particular. And it's actually kind of a great time to be talking about that in a great place. We're very cognizant of the history, be able to talk about a lunar lander 50 years after Apollo 11 landed on the moon. It's also great to be talking about it right here when the Apollo 11 command module is 5 to 10 miles up the road. So it's just, all of that comes together. So I hope you'll find this interesting. I realize I'm the only thing standing between you and either heading home or the bar, so I'll promise to try to make this as interesting as I can. So let's dive in. So what I usually like to start with Blue Origin is with our vision. And that's quite simply enabling a future where millions of people are living and working in space. So we believe we want humanity to continue to expand. We want abundance. We want to be able to take full advantage of the near limitless resources of the solar system and be able to preserve Earth. And we want to have a vibrant space ecosystem. And these millions of people living and working in space are enabling that to happen. That is the future that we want to enable. Now, while we don't know what that future is going to look like exactly, we don't quite have that crystal ball, we do know that we're going to require two things that are going to be extremely important no matter what this future looks like. So the first is radical cost reduction. And the cost of launch, primarily right now from the surface of the Earth up into LEO and beyond. Right now, to do anything of any economic significance in space requires millions, if not hundreds of millions of dollars, because a cost of kilogram to be launched into space is tens of thousands of dollars. That's just, many of you are even more aware of this than we are with the business cases you're trying to close. That just provides such a high bar to the ROI of any business case that has to take place in space that it stifles the innovation of this industry. We have to break that. We have to get to a radical reduction in the cost of launch. The second is that we have to start relying much more on in-space resources. Right now, almost every time we go up into space, we're taking all of our propellants for all of the transfers we want to go do. We're taking our air with us. We're taking our habitats. All of that we bring up with us every time, except when we go to the space station. We don't do that here on Earth, usually. If you're going to Paris on a trip, you don't take your hotel with you, your water, your croissants, your red wine. You actually rely on France providing you all of these things. And so you have a much more enjoyable trip and a longer and more affordable trip than you would have otherwise. So that's the mindset we have to start going to in space. So Blue Origin is working on both of these things. That's how we believe we can build the infrastructure to address both of these and unlock that future. Let's talk about the first one. We believe the way to get to radical cost reduction is to have real operational reusability for launch. Now, what do I mean by real? I mean systems that are able to launch, land, be refurbished, and launch again with minimal amounts of work and effort in between these launches. Vehicles that are able to do so affordably and reliably and quickly, and vehicles that are able to do them over many, many flights. And that's something that may be apparent to us now that that's sort of what we need to do here in our industry, but it's not something that we've historically done in the past. Many of you flew here on on an airplane, perhaps a Boeing, just like the Boeings that are outside here. You were not surprised when you guys landed that we just didn't throw the plane out. In fact, these people came on the plane, they cleaned it, they refueled it, and then other people got on the plane and flew it someplace else. That's the model we want to get to in space. And that's what Blue Origin has been focused on. We started with New Shepard. That's our suborbital vehicle. And that's where we said we're going to take this real operational reusability and we're going to start practicing it. We're going to practice how we design that, how we build it, and how we fly it. So let me tell you a little bit about New Shepard, which we've been flying, by the way, since 2015. So New Shepard, like I said, is our reusable suborbital launch vehicles, goes up to 100 kilometers and back. That's the Kármán line, the official boundary of space. Designed to take 6 astronauts up and bring them back down safely. We've flown it 11 times, successful missions. Landed the booster over and over and over. We've had 2 boosters so far that have been flying. Each of them have landed successfully 5 times. We've also done 3 escape tests to make sure that the capsule is going to be safe under a whole host of conditions. So we did a pad abort test. We got the capsule safely back. We did one at max Q right there. By the way, that booster actually landed back down safely, even though we aborted off of it. It's actually in our facility in Florida now. And then we also did an abort off of the booster at Apogee as well and landed the capsule safely. So the capsule has done 12 successful touchdowns, and again, because we're counting the escape test as well. And it's always really nice to see it coming back under those chutes. We've done it where we've actually tested with shoot-out capability and had it land safely as well. I don't know if you can see our mannequin Skywalker in there in some of the windows, but they are the largest windows to have ever flown in space. So we've built New Shepard to actually have a suborbital tourism market. Like I said, we're going to be flying astronauts on there, eventually 6 astronauts up to space and back. We've also been flying a lot of suborbital payloads, primarily with NASA as part of the flight opportunities. We've actually had multiple commercial flights there for those payloads that have been almost completely full. And it's one where we've also included a lot of universities and a lot of commercial partners. And that, what we see is it's a great opportunity for folks to actually test some, whether it be science experiments in zero-G, where you can get several minutes of high-quality micro-G, or whether you're trying to test some mechanisms or systems that you actually, before you actually fly them up into space, you get to try them out suborbital. It's quite affordable. You get your systems back. So we believe there's a real market for these, and that's what New Shepard's been built. But we've also built New Shepard with an eye towards learning and practice, because we knew we were going to build larger vehicles, and we knew as part of our vision we're going to need way more capable systems. So we said, all right, we're going to make some design choices that we perhaps would not have made if you were just building a suborbital vehicle. So for example, we chose hydrogen as a propellant. Hydrogen's great, high performance, that's sort of why you want it, but hydrogen is sort of also a real pain to work with. It's extremely cold, it does all sorts of bad things to metals and valves and tanks. Hydrogen engines are more difficult to build, but we knew we had to master hydrogen. And so we learned how to design and build all of the associated systems as part of New Shepard. We also chose vertical takeoff and landing. Now, you could have many choices. I mean, our capsule lands via parachutes. We could have chosen that for the booster or wings. But we chose vertical takeoff and landing specifically because it scales much better to larger systems. So if you ever try to actually balance a broom on your hand, it's much easier to balance something small as this, and I'm not going to try because I actually dropped this last time I did that. But it gets much easier as you actually go larger. So We chose that as a design choice. And finally, we started with a system that was rated to take humans up. We knew we had to figure out how to design in human safety while keeping the system affordable and highly operable. And so we went about laying in a whole methodology as to how one does that, and we wanted to make sure we learned that on this system. Why? Well, because we knew we were going to build something that's much larger. And let me show you. So those are to scale. That's our motto, by the way, Gradatum Ferociter, step by step ferociously. New Glenn is that next step. New Glenn is about the size of a Saturn V rocket, actually. You could fit New Shepard in the fairing of New Glenn, just as a size comparison. That fairing is the largest commercial fairing out there. It's 7 meters in diameter. That vehicle there on the right has about 4 million pounds of thrust on takeoff. So it's quite large. And it takes all of the learnings from New Shepard and incorporates them in so we can get to a highly operational, reusable vehicle with New Glenn much faster than we would have otherwise. So let me show you a little bit more about New Glenn here. Again, I'm sure many of you have already seen this and perhaps know it, but New Glenn will launch out of Florida, out of Launch Complex 36. You see it right there taking off, and you're going to see our manufacturing facility right there. That actually is completely built. Our engineers have moved in, and we actually have many of the tooling there to build a New Glenn already in. You see liquid natural gas being burned on 7 of our BE4 engines right there on the first stage. Separating, that's the second stage. That's 2 BE3U engines. That's the upper stage variant of the same hydrogen engine that we fly on New Shepard. That allows us to take 35 metric tons to LEO, 45 metric tons to LEO, 15 metric tons to GTO. In the meantime, the first stage reorients itself, comes back in the atmosphere. You saw some of those aerodynamic surfaces. The fins and the strakes allows you to get some control there and authority so that you can actually get some cross range and land on a moving landing ship. The landing ship is moving because it gives it much more stability while it's underway, allowing us to land in much, much worse sea states and still be able to secure the vehicle. Now, why have we made all of these choices? We made them because we know these customers right here on that second stage are going to want affordability, reliability, and high availability. So we know that these things are not going to change 10, 15 years down the future, and those were all designed into New Glenn. That's part of the reason why New Glenn is a single configuration vehicle. We don't have solids. We don't have different fairing sizes. We want to fly the same thing over and over and over because it's safer, because we get much more practice with it, and because our customers like that. And so we're going to be serving the national security space market. We're going to be working with governments and NASA and other civil space. We're also extremely excited about working with the commercial sector. And that's from the large operators to many of the smaller, more nimble NewSpace companies with their smaller spacecraft. So the whole range, the whole gamut, we want to enable your business cases. We want to make sure we make it easier for the investor to look at your business case and say, oh man, all right, I see these numbers closing. We're able to make these numbers work, and the ROI is there. That's how we measure success, is by enabling all of these markets. So that was the first gate we talked about. The second one, if you recall, was the use of in-space resources. And we believe the best place to go is the moon. Why the moon? Well, since Apollo, since 60 years ago, we now know that in addition to all the great things you have in regolith, not just the regolith itself, but also all of the metals that are embedded there, we also know that there's highly likely to be water ice in the South Pole, something we didn't know back then. And that's going to be extremely valuable. not just for the lunar surface activity, but across this lunar space. All of these materials are available in a gravity well that's 1/6 of that of Earth. So that means it requires 24 times less energy to get up into orbit than you would equivalently from Earth to orbit. The moon is also always 3 days away. It's always there for us. Unlike, let's say, near-Earth asteroids or other places where the launch windows are much, much more constrained, we can get there all the time, and we can set up a reliable supply chain from the moon. Now, in order to get that supply chain in place, we need infrastructure. We need a way to get down to the moon and get back up, and we need a way to put large infrastructure there affordably. That's why we started working on Blue Moon almost 3 years ago. The colonel, and I don't know where he's sitting, but you talked about our founder and sort of the unveiling. So we unveiled Blue Moon and talked about it quite a bit on May 9th, but we've actually been working on it for quite a while. Very excited to be talking to you a little bit more about it here, so we can jump in and sort of geek out a little bit. The first thing I want to talk to you about is our BE7 engine. So you see it right there. That's the green flame as it sort of starts up with the igniters, but then it actually goes to almost an invisible flame right there as it basically outputs steam from firing oxygen and hydrogen there. It fires for 30 seconds. This is the BE7 engine, the same engine we've been developing to put on the lunar lander. That's at Marshall. We're extremely excited to be working with them. They've really helped us move very quickly here. And we fired the engine, as you see here, when we launched this, for about, there we go, and we just shut it down safely for 30 seconds, learned a lot. And what hopefully we'll show you soon here as well is a full 6-minute firing, which we did just a few days ago, for the full duration of the actual BE7, the full 6 minutes. Very excited. That means we're getting a whole lot closer to getting that engine fielded. And as you guys know, propulsion, the rocket engines are extremely important and usually the long pole in the tent whenever you're trying to develop a new system and bring it online. So we're very excited about the progress we're making on the BE7. So what else to note on the lander? You can tell one of the largest aspects of it are these large hydrogen tanks. We chose hydrogen again. We've been practicing on it. We knew we needed it. We chose hydrogen because of the high performance. So it allows us to land much more cargo, much larger ascent vehicles for crew than you would otherwise. Hydrogen also allows you to do some interesting things. So we actually use the hydrogen from the boil-off to cool the oxygen tanks and actually avoid a significant amount of boil-off on the oxygen tanks. And then the fact that we use hydrogen and oxygen means that in the future, once we've set up all this infrastructure, and once ISRU is up and going on the moon, we can actually start refueling this lander using locally produced resources. So now we're starting to meet that second objective of actually using what you have there instead of having to carry everything down with us and back up again. That's how we get to a more sustainable architecture. The other nice thing about hydrogen and oxygen is that once they boil off, we actually collect them in these accumulators. You can see the oxygen accumulator right there on the right, and the fuel cells just below them in those gold boxes. We can actually generate kilowatts of power that are used not just for the lander, but for the multiple payloads on there. So we're able to provide much more services. We're able to help these payloads actually survive even part of the lunar night and actually keep their heaters on and keep operating. Things you wouldn't be able to do with just solar arrays. So hydrogen is a bit of this gift that keeps on giving, so to speak. The other thing about the lander and sort of our design choice is that we went with a very large flat top deck. That top deck gives you a lot of versatility in the kind of payloads you can actually take down to the surface. So you can take large monolithic payloads, you can take large pressurized rovers, you can take smaller disparate rovers, you can unload a whole host of things. And then what you also see up there is the davit system. So it's based off of a maritime system for deploying lifeboats sort of very reliably and safely. And that is customizable to the size of the payload that you have and how many of them. So you actually are able to then reliably get these payloads off of the top deck, which sits about as quite high, so it allows you to really kind of get them down safely there once you land on the lunar surface. So there's a lot of versatility there in this sort of cargo variant that we've built to enable a whole host of missions. Now let's talk about the human variant. So what we've done, as you can actually see, is we've sort of added a section to the lander, because what we've done is stretch the tanks so that we can carry more payload down to the surface, and that's the ascent stage that you see up there. The stretch tanks allow you to do that. But in every other way, this is very much the same lander, and that allows us to have commonality and to get there much faster. So we're very excited that we have the administration and NASA very much aligned on a goal of landing both a male and a female astronaut, Americans, on the lunar surface by 2024. We've been working with NASA as part of the initial studies that they've laid out. We're very excited to be getting going and actually moving forward on landing by 2024. We look back at how Apollo did it, and it's so inspiring to see how that happened. And I think it would be just the career highlight of so many of us to get a chance to do this. So we're just pumped. We want to get going. So let me show you a little bit of what a mission could look like. And I'm going to show you a cargo mission here. So we imagine this as one of the precursor missions that we would go send out. So this is actually based on actual trajectories and mission data as we've designed it so far. So you see the lander kind of getting into low lunar orbit. We actually have so many payload bays. We're able to deploy folks on the way to the moon as well as lunar orbit. That helps deploy a lot of infrastructure and science. You see the engine here firing for the first time to drop our paraloon to get us ready for powered descent. And then when powered descent starts, again, like I said, 6 minutes long. That's how long the BE7 is going to be burning, just like the test we just did. That slows us down. In the meantime, our terrain relative navigation sensors are scanning and allow us to land with significant accuracy, less than 25-meter error. And that allows us to land precisely so we can pre-position infrastructure and use it for future missions. So that way, every landing that we do is adding to the infrastructure and to the assets we can use on the surface. Here's an example of us, let's say, deploying a lunar prospecting rover of some kind. So it's going around and actually finding that water and other resources that we want to go find so we can start deploying the next set of infrastructure to harness that and get it ready for the time when we're going to have the humans come down. So we've started. We've been working on this for 3 years. We want to get going. We want to get there. Now, what I've showed you relies on a whole host of innovation, not just in the actual design of not just in the actual technologies of the lander, but in how we actually even get to that lander. There's a host of innovation that's happening in design, production, and flight operations. And this is not just for the lander, but across all of the systems we're pulling on. So New Shepard, New Glenn, engines. The way we've done it to date has been revolutionized by machine learning, AI, robotics, autonomy. If you think of design right now, we have the ability to run massive amounts of parallel simulations using both local and cloud computing that allow us to basically measure every single edge case be able to test autonomy algorithms in all sorts of conditions and have constant Monte Carlo simulations that really allow us a certain amount of design robustness that we've never had in the past. Production, if you look at how we built Saturn V and the F1 rocket, those machinery are works of art. They are handcrafted. They are built with such precision. There's over, just in the F1, a single F1 engine, there's over 1 million hours of hand welds. We actually can't do those hand welds right now, even if we wanted to. We've lost the ability to do that level of sort of precision welding piston production with that kind of labor. And so we've sort of pivoted in many ways to a brand new type of production that uses much larger format castings than we've ever had before. The ability to use sort of precision computer-controlled machines to do cutting and subtraction of parts into quite complex shapes. But was also, we started using additive manufacturing to build parts made out of both standard and exotic metals and alloys in sort of configurations that have never been even possible before. And that just allows lighter weight, fewer hours, much tighter quality control. There's a whole sort of revolution that's happening with how basically aerospace production is happening. On flight operations, new Shepard is rolled out of the barn, launched, landed, and recovered with a crew of less than 30 people. That level of autonomy is something that has not been possible before. When we fly New Shepard right now, and when we have astronauts on board, none of these guys are going to be, or gals, are going to be pilots, right? It's all completely run via autonomous algorithms, and we have that confidence because of the advances in AI and autonomy. Now, as exciting as these things are, we're just barely scratching the surface. We want to get to a point where if you think of design, you're using AI to scan every single part that's ever been designed. And so when you're trying to design a part, the AI is actually suggesting to you how you can make your part better. That's something that isn't really done right now, and we need to start getting in there. When we talk about production, we generate so much digital data in any production environment right now, and it's sort of really just kept in these different silos. What if we could actually fuse it all together? So you have algorithms that are monitoring everything from the status, the in situ monitoring of everything in the production that's happening, the environment in your production, where the part has come from, who's on shift, whether a quality incident has happened, and integrate all of that data so they can actually figure out all the conditions that enable you to make quality parts and to actually identify and correct ahead of time deviations or nonconformities. That's a level of digital production and integrated production that doesn't exist right now, at least in aerospace. We need to start getting there. And in flight operations, we want millions of people to be living and working in space. We don't really want billions of people here on Earth sort of in their mission control managing them. We need to get to a completely different operating model of how we do flight operations. And so a point where I can tell, we'll be able to tell a lander, hey, land on that part of the moon, and it figures it out. Or go dock with that propellant depot. And of course, you have a constraint-based autonomy, so you have to dock with the propellant depot, make sure you don't run out of fuel, make sure you don't impact the propellant depot, make sure you meet these sort of conditions, and then the vehicle figures it out for itself. We don't yet have that level of trust in autonomous algorithms, but we need to get there. And so one of the things I might ask this community is, I know a lot of NewSpace is focused on, okay, how do we operate and how do we have all these assets in space? But I think there's a lot of innovation and there's a lot of potential for startups and innovation even before you get there, in design, in production, in flight operations. And so that is something that would be of extreme interest across the entire industry. So at Blue, we're all about humans. We want to put humans in space, millions of them. We also want humans to be building not just the rockets, but we want them to be building a company that can be building rockets. Because we know this is going to take a long time to get there. And so we continue to hire. It's going to require some of the best expertise in the industry across a whole host of fields, from software to AI to all sorts of engineering and other forms. So we're always on the lookout. When I joined 2 years ago, we're at just about 1,000 people. Now we're at 2,200 and still growing. And we continue to add folks in Alabama, where a rocket factory, where a rocket engine factory is, and in Florida, where our new Glen factory is going to be, as well as here in Kent. So please, consider us. But I also say, consider also how you can be part of our ecosystem too. You know, we know Blue Origin is not going to be the only player here. We want to be enabling others. My goal is when we get back together here, let's say it's in Seattle in 5 years, to have a room that's 5, 10 times bigger than this, filled with people that are all enabled by what we've been able to do here. And that hopefully we've had our first, I don't know, billion or trillion dollar company that's, you know, based in space and able to drive all these operations. That's what success looks like for us. And a community with that kind of ecosystem is what we're striving for. Now, we know this is a journey. We're not going to get there immediately. It's going to take quite a while. Millions of people living and working in space is not going to be overnight. So part of that reason is why our founder announced Club for the Future. And that is a club meant to inspire and engage the future generation. And we know our job is going to be to lay out this infrastructure, to start putting the building blocks in place. These are going to be the folks that actually build upon that infrastructure, continue down that road, and hopefully put into place all of these great ideas that we've all had, and they've been sitting, you know, on shelves and paper since the 1950s, and actually put them into practice and start crafting this future of millions of people living and working in space. One thing I would strongly encourage you guys, or if you have kids, is we will send your postcard to space. Grab a postcard, write your hopes, your dreams, some space doodle, send it to us. We will fly it on New Shepard, and we will mail it back to you. And then you can have something that's flown in space and use that to inspire yourself, to inspire your kids, other people's kids. We need to build the community, and we need to build something that's going to be long-lasting here. So I want to thank you guys for taking the time to learn a little bit more about us. We are extremely excited, not just to be working on the launch infrastructure and basically the all of the infrastructure to help you get to your business case, but also to be able to build upon the shoulder of giants. The folks that launched to the moon 50 years ago and returned back safely. And we have an opportunity here to do the same and actually have this be sort of the start of an ecosystem that continues and builds upon itself towards something that is, really enables us to get off this planet and have millions of people in space. So I hope all of you get engaged with us. I hope all of you really kind of come along with us with this journey. So thanks again, and hope you enjoy the rest of your time here. Thank you.